Hey everyone, this is the Chapter 6 review video. In this video, we're going to go over centripetal acceleration, how to use Newton's law for circular motion, and then Newton's law of gravitation. First, centripetal acceleration. Whenever something is moving in a circle, it has a centripetal acceleration that points towards the center of the circular path. This acceleration is given by v squared over r, where v is the speed and r is the radius of the circle. As we can see from the picture, the acceleration points towards the center, and the velocity is tangent to the path at any time. Let's look at an example. What is the acceleration of a car moving in a circular path at a constant speed? We're used to a constant speed, meaning that there's no acceleration. However, when you're moving in a circular path, you always have this acceleration. So the answer would be that we still have this centripetal acceleration. Even though we're moving at a constant speed, we're not going at a constant velocity because we are changing direction at every point along our path. Next is centripetal force. Whenever an object is moving in circular motion, we want to use Newton's second law for circular motion to solve problems involving force. The first step is going to be to draw the free body diagram for the moving object. Next, when we look at this equation, it says that the sum of all the forces equals mv squared over r. This is just ma, since a is v squared over r. To use this equation, we do it a little bit differently than Newton's second law for linear motion. We want to look at all of the forces in our free body diagram. Whatever forces are pointing towards the center are going to be positive. And whatever forces are pointing away from the center are going to be negative. Once you know that, then you're able to set up Newton's second law and solve problems. Let's look at an example. Find the friction force on the coin. Now, assuming it's moving at a speed v and that the distance from the center of the circle is r. The first step is to draw the free body diagram. If we look at the top view of this coin here, we know that there must be at least one force pointing towards the center of the circle. This is always true whenever things are moving in a circle, because if there's an acceleration pointing towards the center, there must be a force. In this case, the force pointing towards the center of the circle is a static friction force, which prevents the coin from slipping as the table is rotating. Since this is the top view of the coin, we don't need to draw the normal force or the weight of the coin. These go out of the page and into the page respectively, but they don't affect the circular motion because they're perpendicular to the motion. I like to show which way the circle is going so that I can see that this force is pointing towards the center of the circle and it will therefore be positive. Now we're ready to set up Newton's second law for circular motion. The sum of the forces equals mv squared over r. We only have one force, so that means that the static friction force equals mv squared over r. As long as we are given the mass, speed, and the radius of the circle, then we are able to solve for the static friction force. Sometimes when we're solving problems involving circular motion, we're looking for critical speed, which is the speed at which an object is about to lose contact with the surface. This happens when we're moving up on a hill or upside down in a roller coaster. If you're trying to find this critical speed, all you need to do is set the normal force equal to 0 after you have set up Newton's second law for circular motion. Let's take a look. What is the maximum speed at which a car can round the top of the hill without leaving the surface? That's what the question is asking. Whenever you have max speed, that's an indication that you're looking for that critical speed. So the first step is to draw the free body diagram. Draw the car, and then we know there's a weight going straight down. We know that since there's a surface, there's a normal force perpendicular to the surface. We don't include the velocity as part of the free body diagram, only the forces. There could be friction opposing the velocity, but if there is, it's going to be perpendicular to the circle, so it's actually not going to affect the circular motion. Only forces that point toward the center, which are positive, and away from the center, which are negative. Those are the only forces that affect the circular motion. I do like to draw the little part of the circular path just to show which way is towards the center of the circle. So we can totally ignore this kinetic friction force. Now we're ready to set up Newton's second law for circular motion. The sum of the forces equals mv squared over r. We're going to write down the weight, which is positive, and subtract the normal force since it's negative. Those are the only forces. We're done with the left side. We just write down the right side of the equation as it is, mv squared over r. Now, since we're looking for the critical speed, we can set the normal force equal to 0. And we know that weight is equal to mg. So we're going to have mg equals mv squared over r. We can go ahead and cancel. Let me actually rewrite it so it's a little bit neater. mg equals mv squared over r. Now we can cancel out the mass. On each side, we can multiply each side by r to get rid of the r. And then all we need to do is take the square root of each side to get the speed by itself. V equals square root of rg. So that is how you would solve for the critical speed. The important thing is drawing the free body diagram, setting up the equation, and only setting the normal force equal to 0 when you know for sure that you are solving for a critical speed. Next is centrifugal force. This is a fictitious outward force that occurs when an object is rotating. Now, it occurs when you are in the rotating frame of reference. Let's look at an example. We have a person spinning, and there's a ball attached to a spring. And then we have another person standing on the side. What's the direction of the force on the ball? So it actually depends on your frame of reference. If you're the person, the observer on the outside, who's not accelerating, you know that the spring force is pulling the ball inwards. And that spring force is providing the centripetal force so that the object can move in a circle. However, if you are the observer who's rotating, it seems to you as though the ball is being pulled outward. That outward force would be a centrifugal force. This is a fictitious force, and you should not include it in the diagram. You should always draw the forces on the diagram from the view of an observer who is not rotating. Finally, Newton's law of gravitation. This law tells us that there's a gravitational force between masses, and it's given by g, the universal gravitational constant, which has a very small value, the product of the two masses, and the distance between the masses squared. So whenever there are masses, there's going to be this force between them. This force is attractive. It pulls the masses together. Let's look at an example. What happens to the gravitational force when you triple the distance between the two masses? Whenever we have this type of problem where you're changing a variable and seeing what happens to another, I like to write down the original equation, which is right here. So I'm not going to write it again, but we have it right here. And then I'm going to write the equation again and change whatever variable has changed. So the new gravitational force is going to equal g, the product of the two masses, which has not changed, and the distance is now 3r. Make sure to square the whole new distance. That's the trick here. Go ahead and do the algebra to simplify this. We're going to have g m1 m2 over 9r squared. Go ahead and bring the factor of 1/9 to the front. We're going to have 1/9 g m1 m2 over r squared. When we write it this way, we can see that the new force, when you triple the distance, is 1/9 times the original force. So we can see that increasing the distance between masses is going to reduce that gravitational force. And that's it for this Chapter 6 review video.